If you're watching this, this is everything you need for tomorrow. Okay, so everything in fluids that we've talked about. Where did we start in fluids? Well, we started fluids with density equals a mass over a volume. And you can play with that equation however you'd like. We also talked about the idea of pressure. Pressure is equivalent to a force over an area. If you're at the bottom of a fluid, then the pressure due to the depth that you are at, and we'll call this some value h, that pressure is equal to rho g h. If you would like to know the difference in pressure from one height to the next, we'll call this a delta h, and the change in pressure, or the difference in pressure there, is equal to rho g delta h. Recall that if you are at the bottom of some pool here, your pressure is not just due to the rho gh from the surface on down. This is just a gauge pressure. It's just the pressure from one substance. If you want the entire pressure, you need to include the atmospheric pressure, which in chemistry they would just call 1 atm, which is a not real unit in my opinion. This is 1.01 times 10 to the 5th pascals, and then you would add it to the rho gh. So the total pressure you'd have would be the atmospheric pressure plus the gauge pressure. This is why if someone ever knifes your tires, the pressure in your tire isn't zero. The gauge pressure on your flat is zero. There's still an atmosphere worth of air inside of it. So that's where we talked about with pressure there. We also spent some time talking about if you have objects that are floating. When we had objects that are floating, like our many boats, like the Going Merry, it's a boat. If we have a boat and it's floating, what causes that boat to float? Well, the buoyant force, FB, that's equivalent to rho GV, where this rho is the density of the fluid or the liquid that you're in, G is gravity as always, and this volume is the volume that is displaced by the boat. So it's only this volume that is actually displacing water. Because that is the actual fluid that is being displaced, and that displaced fluid allows for that buoyant force, which is acting up on your object. If you recall, we had a few interesting problems that dealt with this. If we had like a cannonball that was on a ship, and then we knocked this cannonball into the water level would actually go down, because now we're not holding the entire weight of that cannonball and having to displace all of this weight worth of fluid. Remember, rho v is mass and m times g is a weight. So this is the weight here of that fluid or the liquid. But now we're just displacing the volume of the cannonball, which is much less. Another way to think about this for objects sinking or floating is, in general, if the buoyant force is greater than the weight, then you are going to be able to float. If the buoyant force is less than the weight, you're going to sink. And if they are equal, then you're going to hold position. So wherever you're at, you're just going to stay there. Okay, it's very similar to you just moving with whatever velocity you had initially, and nothing's kind of happening to you. Okay. Another way to think about if objects are going to float or sink is densities less than one being water in terms of gram per centimeter cubed. Those are going to float. Densities greater than 1 gram per centimeter cube, this is going to sink. This is the density of water, 1 gram per centimeter cube. It is also equivalent to 1,000 kilograms per meter cubed. And that's where we did a lot of stuff with our statics. If you had to do a problem with this, maybe you'd want to recognize that, you have a buoyant force here. Maybe there's another force pulling up, like a tension, and then an object might have a weight going down, and you would just set up an F equals ma. Let's call up positive, down negative. So like tension plus the buoyant force minus the weight equals ma, because that is Newton's second law. F equals ma. Sum of the forces. And that was fluids from a statics perspective. Once we started having fluids begin moving, we had an entirely new world of stuff that we had to conquer. When we had fluids that were moving, we, using the conservation of energy, were able to build a big old Bernoulli's equation. And big old Bernoulli was that P1 plus rho g H1 plus 1/2 rho V1 squared equals P2 plus rho g H2 plus 1/2 rho V2 squared. This equation is super important. We could also write this as the left side equals some constant. However you like to think about that is fine. But that's a super important equation for us. It tells us general ideas of, if we have some pipe here and that pipe expands in some way, how things will change on the flow rates. This equation also tells us that if we have a high velocity, that means that we are going to have a lower pressure, and a slow or a low velocity is going to be a higher pressure. So if we had something like, imagine we had some sort of tube thing here like this, right? So here's like a tube. And then in the center of the tube is some amount of fluid. Okay, maybe like the fluid sticks up to here. If you took this fluid and you put it through here going very fast, what would actually happen right here where that fluid is moving fast is you'd get a low pressure, and this would actually be pushed down in this case. Kind of interesting effect there. You could get a kind of opposite effect if you had a very similar setup to this, where we kind of draw it like this. Where in this case, if this is like submerged in a thing of water, like if this is in a thing of water like that, if you sent the fluid through here moving very fast, you would actually pull the water up a little bit, because this would be a low pressure and on the outside would be a high pressure. You would push the water up, so the water would be at some new height here. These are known as Venturi tubes, which we only briefly, even brought up in class. We also have to remember that while we do have big old Bernoulli's equation, we also have mass continuity, which is that the area multiplied by a velocity equals some output area multiplied by that output velocity. This is the thumb that you put on a hose. It is very important to remember that area here is equivalent to pi r squared, which means that if you double your radius, you actually increase your area, or that cross-sectional area there, by a factor of 4. Tripling your radius ups it by a factor of 9. Quadrupling it is a factor of 16. Okay? So if your area goes up by a factor of 16, because you quadrupled the radius, your velocity is going down by that amount. So keep that in mind. This is a squared value right here, which affects both of these areas. Very important thing. It was actually an intergalactic problem. A number of people mess that up. Most people, when they look at this, they go, oh, I just doubled the radius. That's doubling the area. Incorrect. You doubled the radius. You have squared it. So 2 squared is 4. You've changed your area by a lot more. So that was the mass continuity equation right here. And if we took big old Bernoulli's equation and we made some assumptions, maybe we were in the old western town and we had a large water tank that was up on stilts and a hole was shot in the bottom of it such that the water was coming out. If we assumed that the pressure up top and the pressure at the side are the exact same, then these P1s and P2s become eliminated. And if we assume that this hole on the bottom is so small that the velocity of the water going down is essentially 0, this part of big old Bernoulli is eliminated as well. When we eliminate those and then rearrange this equation, we find that the velocity of the water coming out is equal to the square root of 2 times gravity times delta H, where this delta H is the difference between the top of the water and wherever that hole is. This will give us the ejection speed of the water coming out of that vessel. If you wanted to figure out how far that water went, whooshing, you would need some delta Y here. And the way we'd get that is using the kinematic equation of time. We've actually shown in class a proof of this, but in general, if you're looking for delta X for like where the water actually went pew, 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 and struck, we saw that we could combine the kinematic equation and this velocity and state that delta X is equal to the square root of 4 times delta Y delta H. And the first student in our class to do that ever was Sir Jacob Metz. So we call it here the Metz equation, but really it's just a combination of kinematics and the Torricelli equation here. So we've got Torricelli, which is an important thing. You need to know that. You need to know how to derive it from big old Bernoulli, and if you don't, you're going to have a bad time. But that right there, everything we've just talked about, that is our unit on fluids. Everything from fluid dynamics to fluid statics up top. And if you could do that, you're going to be fine on the test. And look at that. Only 11 minutes and 30 seconds to get through an entire unit. Once again, it's a wonder why it took so long for us to cover all of this amazing content in our actual class. So with all these equations, best of luck on your exam. And until next time, adios and take it easy.